Now let's talk about the Clausius theorem. Now to understand this, let's put our attention to this diagram first. So just listen to what I'm saying and then we'll build up what is being shown on this diagram step by step. So let us assume a system, and let us say that system is being taken from an equilibrium state I to another equilibrium state F. Okay, by following a reversible path IF. So this is the reversible path we are talking about, this curved path. So the process is from I to F. Okay, now let a reversible adiabatic IA. So these lines, they indicate a reversible adiabatic line, and a reversible adiabatic IA. Let us use some other color. This line. This is IA. Okay, is drawn through I, and another reversible adiabatic BF. So this is the other adiabatic, that is BF. It is drawn through F. Okay, then a reversible isotherm is drawn in such a way that the area under IABF is equal to the area under IF. So the area under IF first, if you look at this, is this. So the area under IF would be this complete area, this pink colored region is the area under IF. Okay, and this area has to be equal to the area under IABF, and let us say that area is the orange colored region. Okay, and that would be this. Let us draw this kind of hatching. So this area. Okay, so these two areas are same. Now if we apply the first law on the process IF first, okay, so let us write down process IF. Let's apply the first law of thermodynamics on this. It says the heat interaction between going from I to F is equal to UF minus UI plus WIF. Okay, and then let's apply the same for the process IABF. Alright, and you will get Q for IABF is equal to, again in the same process, that is IABF, you are still going from I to F. Okay, so you get UF minus UI plus WIABF. Okay, now if you look at this, the area below IABF and the area below IF are same. Now the area below the curve represents the work done. So work IF is equal to work IABF because the areas are same. Okay, so this means that WIF is equal to WIABF. Now you can equate these two equations, and that would lead us to, because they will cancel off these and cancel off these two terms, you would get QIF is equal to QIABF. Now what is QIABF? It is Q for IA, then Q for AB, and then Q for BF. So this becomes Q for process IA plus Q for process AB plus Q for process BF. Alright, now if you pay a little bit of attention over here, QIA is 0 because it is on a adiabatic line. This is also 0. So the only heat left is QAB. This means that QIF is equal to QAB. Now this is the crux of this whole video, that is heat transferred in the process IF is equal to the heat transferred in the isothermal process AB. So this means that any reversible path, in this case the reversible path was IF. So this reversible path, okay, so we will generalize it. So any reversible path can be substituted by a reversible zigzag path. I'll write down this word, reversible zigzag path. Okay, so in this case the zigzag path is IA. Let me use some of the bright color. So yeah, so IA, then AB, and then BF. So this is the zigzag path. Okay, and this zigzag path is also between the same end states. So this reversible path is between the states I and F, and this zigzag path is also reversible and also between the same end states, and it consists of an adiabatic process or a reversible adiabatic process, followed by a reversible isothermal process, and then by a reversible adiabatic process, such that the heat transferred in the isothermal process is same as the heat transferred during the original process. So this is the proof, or this is the inference or the observation we draw out from this whole analysis, that you can substitute this kind of a process for a reversible path like this, and the end states have to be same. The first would be a reversible adiabatic, the second would be a reversible isothermal, and the third would also be a reversible adiabatic, given that the heat transfer between this complete process is equal to the heat transfer between this or during this isothermal process. So I hope you understood this analysis. Right, now let's move on to the next diagram of the same video, that is this. Now, this is quite a scary looking diagram, but believe me, if you understood the earlier part of this video, then this would be very easy. Now in this diagram, let us observe a smooth curve. So this is the smooth curve which represent, now this is curve which is also closed. It represents a reversible cycle. Okay, now let the closed cycle be divided into a large number of strips by means of reversible adiabatic. So these lines are reversible adiabatics. So this is a reverse, or these are all a reversible adiabatic lines. Alright, now the top and the bottom of each strip, so this is one strip, so this line and this line, it makes one strip. So this is one strip, this is the other strip, third strip, fourth strip, like this and so on. Okay, now the top and the bottom of each strip is closed by the means of a reversible isotherm. So this line over here is a reversible isotherm, and this is also a reversible isotherm. Similarly, if you draw over here, so these are also reversible isotherms. Alright, so this is also a reversible isotherm. So very simple arrangement. You have a closed cycle, a reversible closed cycle, and you divide it into a number of strips with the help of reversible adiabatics, and the top and the bottom of each strip is closed by a reversible isotherm. Alright, now if you look closely, if you just observe this arrangement, this arrangement, this much, is nothing but a Carnot cycle. So we have divided up the original cycle into a number of small Carnot cycles. So this is one Carnot cycle, this is the second Carnot cycle, okay, like this. So you have so many number of Carnot cycles which or you can say which are replacing the original reversible cycle. Okay, now let's number these things. So let us say this point is A, this point is B, this point is C, and this point is D. Now this isotherm is temperature T1, Alright, and the bottom isotherm is temperature T2. Okay, now the heat absorbed during the isothermal expansion is, let us say, dq1, and the heat rejected during isothermal compression is dq2. I hope you all remember the Carnot cycle. Okay, so this is what is happening, and there is no heat interaction during these paths because these are adiabatic paths. Okay, so I can write down that for an elementary cycle A, B, C, D, okay, heat dq1 is absorbed at temperature T1, is absorbed at temperature T1, and dq2 heat is rejected reversibly. So both absorption and rejection are being done reversibly at temperature T2. Okay, now you can say that dq1 by dq2 is equal to T1 by T2 because it is a reversible heat engine or a reversible cycle, and from here I can get that dq1 upon T1 is equal to dq2 upon T2. So let us put this expression into a box. Alright, now if the heat supplied is positive and the heat rejected is negative, so you would have dq1 as positive and dq2 as negative. So this would become dq1 by T1 is equal to minus dq2 by T2. Now if you rearrange it algebraically, you would get dq1 by T1 plus dq2 by T2 is equal to 0. Again put this into a box. Okay. Now similarly, let us take the second elementary cycle, that is, let us say this is E, F, this is G, and this is H. Alright, and the amount of heat that you get in is, let us say, dq3, and the amount of heat that you reject is, let us say, dq4. So for the second elementary cycle E, F, G, H, you get dq3 by T3 plus dq4 by T4 is equal to 0. So similarly, you have so many cycles like this. So if you add all these equations, you would get dq1 by T1 plus dq2 by T2, okay, plus dq3 by T3 plus dq4 by T4, and so on, and this all adds up to 0. So this is something we get when we add this expression for all the elementary cycles. Okay, and this sum is basically for the whole cycle or for the original cycle. Okay, and if you write it down as an integral, you get for a reversible cycle the integral, cyclic integral for the term dq by dt, it is 0. Okay, thus this means that the cyclic integral of dq by dt for a reversible cycle is 0. Now this is known as the Clausius theorem. Okay, so let's define the Clausius theorem now. That the Clausius theorem, it says that the cyclic integral of the term dq by t for a reversible cycle is always 0, and this is how you represent mathematically the Clausius theorem. Okay, and it is only valid for a reversible cycle. So this R, it emphasizes that this is only true for a reversible cycle. So I hope you understood this concept of Clausius theorem and how did we analyze this theorem. Now, after having understood this, let's go on to the next video and define the property of entropy.